Welcome everyone. In this video I'm going to talk about the Peltier cooling again and cooling in general, because I saw some misconceptions or bad ideas about cooling and Peltier cooling in general. So I would like to try to clarify those things, and I would like to give you some better ideas about how these things work and how these things can be used properly. So you can see a few objects here, and I would like to use them as some sort of demonstration tools. And also you can see the Peltier cooler here and the CPU cooler that I'm always using in my experiments. So I would like to use them and show a few things by them. So first of all, let's talk about cooling in general. So what is cooling? Cooling is when you decrease the temperature of something. And that can happen in two ways. One can happen without any kind of assistance, and in that case we say that it's a spontaneous cooling, and that happens in everyday life. So for example, if you make a huge pot of soup and you leave it on the kitchen's counter, at the end of the day it will reach the room temperature. So it will be in a thermal equilibrium with the kitchen, or with the kitchen's environment. So this is spontaneous cooling. And then you have a, let's say, non-spontaneous cooling, and that happens, well, still in the kitchen. When you look in your fridge or look in your freezer, that's where you can find this kind of non-spontaneous cooling. And why is it non-spontaneous? Because you have to introduce work into the system in order to realize that cooling. So what you do is you run the compressor inside the freezer or fridge, and this compressor will do a work on the gas or liquid, which can be found in the cooling system of your refrigerator. And due to that work, that gas or liquid will go through phase changes and so on. So it will essentially pump out the heat from the inside of the fridge or freezer, and by this it will decrease its temperature. But this is not spontaneous, so you have to introduce the work. So if you look at these two things, you can see the following. So when we take the hot side of this Peltier cooler, which is 4 by 4 centimeters large in surface area, so 16 square centimeters, you can see that this is a relatively small area. And the cooling is better when you have a large surface area, right? So why? Because if you have a larger surface area, then more air from the environment can interact with the surface that you try to cool, and then the heat transfer will be better. Because of course the more molecules, more air molecules hit the fins of the heatsink, the more heat can be transferred from the heatsink. So that means that this hot heatsink can become colder more easily if you have more air hitting it. And that's why you install fans on heat sinks, but let's just not run that further away. So first of all, we use heat sinks to increase the surface area. And in this case, you can see that one layer or one fin of this heat sink is roughly the same area as the total surface area of this Peltier cooler. So you can see that we have roughly 25 or 30 units per side. So this is like 60 times more surface area than this. That means that you can transfer the heat between the hot side and your environment much more efficiently. But in the ultimate case, you will only be able to reach the room temperature on the hot side of this thing, because you don't put any work in this. What you do is just extend the surface area of this. This is just an extension of the hot side. of the Peltier cooler. And the same applies if you turn on the fan. The fan doesn't do anything else, it just increases the volume of the air passing through the fins, and that means that there will be more air in contact with the surface that we have here, and the cooling will be quicker basically. Or you can maintain a lower temperature but still above the ambient temperature, or still above the hot side temperature here, because this is still a spontaneous stuff. So we are not pumping heat anywhere. That's where it becomes non-spontaneous. So this is, again, just an extension of the hot object that you try to cool down. So the cooling in this sense, when you have spontaneous cooling, only means that you cannot cool your object attached to this part lower than the surrounding temperature, the room temperature. So whatever you do here and whatever you try to achieve, this will not cool down, for example, a cup of water to 0 degrees, because that's not how thermodynamics works. It's basically, this is described by the second law of thermodynamics. So the heat always flows from the hotter object to the colder object. And then that means basically that when you have this at a temperature which is higher than the room temperature, and if you run the air through it or just let it sit by itself without any kind of fans, then the heat will flow from this hotter object towards the air in your room. So this will be colder, but it won't be colder than the room temperature. And in the very end of this process, if we idealize everything, the final status of the two systems, so this and the air in your room, will be in thermal equilibrium, and that's all. And by the second law of thermodynamics, you are restricted pretty much that you cannot, for example, if you put your cup of coffee here, it can spontaneously reach the room temperature, but it will not continue cooling down below room temperature. This is basically the very, very simple and maybe popular explanation of the second law of thermodynamics. The coffee will not cool itself below ambient temperature. And also, it works the other way around. So if you have your room temperature coffee here, it will never become hot by itself. So the delta T can never increase. So also, if you start from the hot coffee and you go down, let's say from 80 degrees, and you go down 75, 70, it will not go up to 75 and then go down again. So there is a direction to these processes. And everything is basically related to the entropy. So as you, for example, let the heat flow, then you increase the entropy, or the entropy goes up. So this is one type of cooling, when you have no work introduced into the system, so everything works spontaneously, but you are limited to your room temperature or the surrounding temperature, because it can happen that you have like a semi-closed system and then you have a bit more restrictions, but that's like complicating the things. But if we imagine that we have our very large room available, then when you try to cool something down, whatever happens, you are always limited to the room temperature. But then, so this, the heatsink is just maximizes the contact area between the object that you want to cool down and the cooling media. In this very case, the cooling media is the air. And by default, if you don't use the fan, then you just have a very limited amount of air that is being in contact with the heatsink. So the cooling will be slow and not too efficient. But then if you turn on the fan, As I said, you increase the number of air molecules being in contact with this heatsink or interacting with the heatsink, so then you will be able to remove more heat. But you will never be able to remove so much heat that you will actually cool down the object here below room temperature. Not with just a fan and just the heatsink. So I got a question that it was something like, why do I need the radiator and the Peltier cooler, and don't they serve the same purpose? And no, and that's where we draw the line. So this was the spontaneous cooler, and this is a non-spontaneous cooler, and this is a heat pump. So you have to imagine this thing as this guy here. So this is a heat pump, and I would like to show you some fun analogy. So let's look at these two systems. So let's divide it. So this will be related to the heat flow, and this will be related to the water flow, but they are analogous to each other, which means that I can explain everything with water, and that can be sort of applied. That can be applied on this kind of system. So the water flows in the same way as heat, let's say like that. But let me show what I mean. So we have the heatsink, and that can be, let's say, explained by this hose. And then we have a water pump, which can be substituted with a Peltier cooler as well in our explanations. So let's imagine, I will put a drawing here. Let's imagine that we have two buckets, and we have one bucket that is filled up entirely, so the water level is at the same level where we have the top of the bucket. And then there is another bucket next to it. And this bucket doesn't have any water in it. So let's say that the empty bucket will illustrate our room temperature. And then the full bucket is our hot object. So now let's use this hose and just plug it into the middle of the bucket, which is full of water. So we plug it in, and there will be a certain amount of water entering to the other bucket. And the other end of the hose is also attached to the middle of the other bucket. So what will happen is that the water will go from the left hand side bucket, which is full of water, to the other, and it will only go until it reaches the same water level on the right side. And this will happen spontaneously, so you don't need any kind of pump. You don't need any kind of work to be done. So, and this happened, let's say, in T1 time. So now if we continue this thought experiment, if you increase the amount of tubes, or you just simply increase the diameter of the tube, but you put the tube at the same spot, you will notice that the water gushes much quicker to the other side than by this small tube. And that happens the same with the heat sinks. So when you have a hot object and you put a heat sink on it, then the heat sink, due to the increased surface area, will help that object to cool down to room temperature quicker. And then if you increase the number of fins on the heatsink, so you increase the number of surface area of the heatsink, like you increase the cross-section area of this tube, then the object will be at room temperature in a quicker time, because there is more area for the interaction between the environment and the system that you try to cool down. But if you go back to the water demonstration, we noticed that the water stopped halfway, and there is still water in the left-hand side bucket. And what happens if we want to cool it down more? Because now these two buckets with the equal amount of water represents the equilibrium between these two systems. So, for example, if this would be your room and something which was very hot introduced to your room, then you increased the room temperature but decreased the temperature of that hot object. But what happens if we want to empty the bucket? So that is the non-spontaneous cooling, basically. So there we will need the pump. So if we introduce a pump and we attach the hose to the bottom of this bucket, then we can move all the water to the other system. But we need to introduce work to the system. And basically this is how Peltier coolers work. So if you take the cables and let's say we have an object, this guy here, which is at a certain temperature, and then we attach our Peltier cooler to it, and then we have the heatsink. If initially, if this container is warmer than the room temperature, and we have everything like this without turning on the Peltier cooler, then the Peltier cooler just acts as a piece of material, and then everything depends on the heatsink. There is no heat pumped, everything is spontaneous. So at the end of the day, this thing will reach only the room temperature. But what happens if we want to go down below room temperature? Or what happens if we want to empty the bucket? So that's when we turn on the thermoelectric cooler or Peltier cooler or heat pump. So then what happens is that we introduce work, so we force the system to pump the heat from the now colder object, colder than the environment, to the warmer object, because again, second law of thermodynamics, you need to introduce work, otherwise you would not be able to pump the heat from the colder to the hotter object. So now we turn this on, and then the temperature of this decreases, and of course the temperature here will increase. So that's how you cool with this. So coming back to the question which I was talking about a few minutes ago, so that's why you need the radiator and the Peltier cooler at the same time, because if you want to reach temperatures below ambient temperature, you cannot use the radiator or you cannot use the heatsink. You can only go down to ambient temperature with these things, and if you want to go below ambient, you have to force the heat to move from the colder object to the warmer object, because spontaneously that doesn't happen, and that's why we have the pump. And again, the analogy, if you want to move the water up to a higher level, you cannot just put a hose there and hope that the water will go up instead of going back down. You have to use a pump. So these guys are the same, but this transfers water and this transfers heat. And that's basically the big difference. So when we have this larger object, it just the same happens. So first of all, let's say we want to cool down this container, and let's say now it is a 50 degrees Celsius container. So we have this, and attached to this. So what happens now is we increase the surface area of this box, and that means that it can cool faster because there is more surface provided for the interaction. But now we are at 25 degrees room temperature, everything is in thermal equilibrium, but you want your container to go down to 0 degrees Celsius. And that won't happen spontaneously. So you put a Peltier cooler there, hot side goes here, cold side goes here. So you attach these two things, and you have to do work. Or not you, but the Peltier cooler has to do. So now you have to attach the power supply, and what happens is that now the heat is forced to go here. And by that, you can cool down the object. So to summarize this whole thing is When you think about cooling, you have to think about the second law of thermodynamics, and you have to go back a little bit and you have to think about the spontaneous and non-spontaneous processes. So, sorry if I repeat it for the 10th time, but you really have to remember this, that with this kind of cooler, you only do spontaneous cooling, which means, once again, that you cannot reach temperatures below room temperature. And if you need temperatures below room temperature, you always have to introduce work, or you always have to do work. And how you do the work is, one thing is that you use a Peltier cooler and you transfer the heat. So this is basically, you see that there is an inlet and an outlet. And that's the same. The inlet is equivalent to the cold side of the Peltier cooler. So the heat goes in, or the water goes in. And then here, inside this, you have the electric motor that moves the water and pumps it towards the outlet. And here in the Peltier cooler, you have the small pieces of semiconductors, the small blocks. And then those, if you run electricity through them, those will pump the heat from the cold side, which is again equivalent to the inlet. They will pump the heat, those small semiconductors, to the hot side, which is equivalent to the outlet. But still, if you imagine that you have this thing and you have a tank attached to this, you still need to put that water somewhere, right? And the same happens here. So now imagine that all the heat is here, but you cannot just, let's say, collect infinite amount of heat on this side. So of course you have to spread the heat like this. So you increase the surface area of the hot side of your Peltier cooler, and then that means that essentially this is like a hypothetical idealization of the system, because of course here you cannot have the same temperature as here. So this side, maybe it will be 50 degrees, but this will be only 35 or something like that. But hypothetically talking, now this whole thing, the heatsink and everything, is your hot side of your Peltier cooler. And now you have a much larger area available to get in contact with the ambient air and try to bring this temperature down to room temperature. So this is how it works, and this is how you could imagine the water heat analogy. So both of these things are pumps, but one thing is moving liquid and this moves heat. So I really hope that this was not so confusing and it worth the effort to try to explain it. And I hope I haven't really messed up anywhere. So I tried to be clear, but it's not so easy because these concepts can be confusing, and it really needs to be explained. So this is a very, very important topic, and it's essential in order to understand how the Peltier coolers work. So these are the real coolers, and these are just heat spreaders, let's say. But this is what it cools. So I think the word cooling sometimes is not interpreted or not used properly, or something like that. So yes, of course, this is a CPU cooler because the CPU is at, let's say, 60 degrees. So with this, of course, you can cool down your CPU because the ambient temperature is just 25 degrees. So in that sense, it's cooling, but we should call this spontaneous CPU cooler. And then this is the non-spontaneous. So if we go back to the CPU, so now let's say that this is the CPU. So if you put this together and your CPU is at a certain temperature, you can keep it at a certain temperature with this spontaneous cooler. But what happens if you want to go below a certain temperature? So, for example, when you try to overclock your device, and that's when this guy comes into the picture. So if you want to cool your CPU down to 10 degrees, you will never be able to do that if you don't have 10 degrees in your room. And most of you, I guess, don't really like that temperature in your room. So then you have to forcefully move the heat with the Peltier cooler. So still you need this cooler because the heat doesn't exit in these wires. It just appears on the other side. So this is, again, just a pump. So what happens here is you have your now CPU, and then you move the heat from this side to this side, and then you need to spread that heat like this. And now you are able to cool down your CPU to lower temperatures. Of course, you will be limited by the cooling capacity of this. So of course, if there is so much heat because of the rejected heat of this device and because of the CPU, then you might not be able to reach very low temperatures. But this by itself cannot go below ambient temperature. So the whole concept of this Peltier cooler can be understood by thinking about going under ambient temperature. So then here now you have this CPU Peltier cooler, CPU cooler sandwich, and then this can force the heat to enter this guy here, and therefore this temperature can drop below ambient temperature. So I hope that this was a good explanation and you could understand a little bit more. I will try to do some more follow-up videos regarding some questions and some kind of ideas. So I hope that you like this, and I will try to make more of this in the future, and we will see how it works. And if you will have more questions, then I will try to catch up with those questions. So I hope you learned something, and I hope I haven't confused you too much. And don't forget to subscribe, please. It helps me a lot, and see you in the next video.